This chapter is about transporting energy and matter, which is what we do in climate models, because in the real world we said we have to move energy constantly from low latitudes to the polar latitudes, because low latitudes are receiving excess energy, more shortwave energy than they are losing to space as long wave, and at the poles it's the opposite, so we have to keep moving energy. And the processes typically involved in moving energy and matter are diffusion, advection, convection, and so on. So we'll start with diffusion. Later on we'll see that this kind of molecular diffusion is basically not that important in climate processes at planetary scales, and we'll see how they are represented instead of molecular diffusion that we are looking at. But for simplicity, for starting the concepts, it's better to start here. So we are looking here at a model of one-dimensional diffusion. The particle density in a cell at xi, so this is, let's say, the x direction with, we have boxes defined as delta x. Each box has some particle number nx at I, and obviously that means number of particles is dependent on x. As you can see, this box has more particles than this one, than this one, than this one, and so on, and we number them as I minus 1, I plus 1. You already know where that goes. So the basic assumption in diffusion is that the probability that a particle will move in any direction is equal. This is what we called, for example, local thermodynamic equilibrium. When we measure temperature, we are assuming there is isotropy, so that particles are moving in any direction with equal probability. So if you have a probability p of a particle moving in any direction, then the number of particles that move across this interface will be written as p times nxi. That's the particle concentration at in this box, and then the next box xi plus delta x, xi plus delta x, or I plus 1, the particles are, let's say, moving in that direction, so we are interested in the net exchange across this interface between box I and box I plus 1. So it'll be flux in this direction minus the flux in that direction, so p times nxi times a delta x, where a is the height or the interface extent, so that delta x is the volume. So you have a times delta x times probability times nxi going in the ith box to I plus first box, and I plus first box has nxi plus delta x. That's the number in the next box, and that has a probability of n times a delta x moving in the negative direction, so that's minus, and that's happening over a time delta t, so a times delta t. So a and delta t is the time at which time over which particles are moving in either direction. So you can simplify that, take a cancel out a, p over delta t, and multiply by delta x, so you get delta x squared, and then you take nxi minus, or you flip the sign, you put the minus sign here, nxi plus delta x minus nxi divided by delta x. It's just a simple manipulation, make sure you understood it. All we did was put a negative sign, so we can flip these and then take p delta x squared divided by delta t out, and this is what we call a diffusion operator, diffusion coefficient, diffusivity, and so on. So in the limit, delta x goes to 0 and delta t goes to 0, provided delta x squared divided by delta t is a constant. As delta x and delta t go to 0, the ratio remains constant, so that you don't go to infinity with delta t going to 0 while delta x is positive, and so on. So we get the Fick's first law of one-dimensional diffusion by doing that, where we're writing the diffusive flux as minus p delta x square divided by delta t times dn dx, where dn dx is basically the gradient of the particles in the x direction. Okay, so even if you had one box and you had some kinetic energy where the temperature was not zero, then the particles are constantly moving around. If there is no gradient, just the concentration, let's say, remains the same, but there is a constant motion of particles in random directions. The so-called Brownian motion keeps going on. But when you have dn dx, then you get a flux which is given by minus d dn dx, which basically means it will be down the gradient. So it goes from high concentration to low concentration, high n to low n, preferentially over time. So even though there is constant Brownian motion, eventually you end up wiping out the gradient with diffusive fluxes. The generalization, unless you maintain it by adding constantly somewhere, the generalization of 3.1 to a three-dimensional isotropic space and a concentration C given by x, y, z, so it's a three-dimensional box with particles distributed in all directions of an arbitrary physical quantity yields fixed first law of three-dimensional diffusion, where now f flux is a vector, and that's equal to minus d, the scalar diffusivity, times gradient of c. Those who have done vector calculus already know what this gradient means. It's basically I times d dx plus j times d dy and k times d dz, or this is a vector of gradient operator. Okay, so gradient of phi x y z gives us d dx d dy d dz of phi, which is a function of x, y, and z. So we get a vector df dx, df dy, and df dz. I think you have done it somewhere. If not, please brush up on these things. Very simple, so I won't go into more details here. By looking at the examples of diffusive flux, rho here is density, mass, for example. Rho s is particle or mass density of salt. So you can say mass flux is minus d times gradient of rho. If there is a density gradient because of salt, temperature, or pressure, or whatever, then you get a diffusive flux. Heat diffuses based on the gradient of temperature, and that depends on density and heat capacity, which tends to be written as lambda, so minus lambda gradient of T. Salt flux is again dependent on gradient of salt, so it's the salt density of salt or density of mass. So this is a density of mass, density of salt. And the y momentum, for example, if you have zonal winds and meridional winds, and the meridional winds are given by meridional gradient is given by du dy, then or u with a function of y, then diffusive flux in the y direction is minus d times gradient of rho u y. Okay, so we will see what this means later on. Basically it means this is d dx. If rho is constant, you can put it out. If not, it will be d dx of d dx of rho u y, d dy of rho u y, rho u y dx, rho u y dy, rho u y dz, and so on. If you only want to worry about the y momentum, then it will be typically written as a v, so it will be dv dx, dv dy, dv dz. Okay, so here is an example. Let's say there is some fluid sitting here and you released some dye or some salt or sugar or something. Then the gradient of the salt or sugar or dye causes Brownian motion of the liquid in which fluid into which it is injected to make it get mixed up. So over time the Brownian motion basically ends up making for a uniform distribution of the salt or the dye or the sugar. Okay, so it's a very simple concept. Probably you've seen it somewhere, but in this context it's better to go through it again, so that when we add energy, matter, and material, other matter and material, the same thing, but we'll see how that gets applied in climate modeling. Okay.